Hi there. My name is Richard Scherer. I live and work in Midland, Texas. And what I'm going to do is I'm going to go through a presentation today on why Midland, Texas is the center of the universe and building a representative type curve to run PHDwin economics for analyses. Now, this presentation, I'll point out, has been specifically put together for PHDwin and TRC consultants upon a request. But fundamentally, the presentation was originally put together 6 years ago and presented in Midland, and then it's been updated on several occasions. And this one here is specific to building a type curve versus the other dimensions of the presentation that were in the prior several renditions of it to the present. Okay, so now what we're going to talk about here is the objective and takeaways from this presentation. I've got 5 things that I'd like everybody who is listening to this to basically gain an appreciation for, and that is to understand the unique geological environment that created the Permian Basin, what characteristics does the Permian Basin have that makes oil companies clamor all over each other, and has ingrained Midland and the minds of OPEC members and every oil minister on the planet. The USGS is another aspect of this Midland Basin presentation that basically has put together some very detailed resource assessments. And I've put together what I would call a very simplistic way of putting together future locations on the basis of what was provided by the USGS. The crux of this presentation is based on a step-by-step methodology of building a type curve to economically model future Permian horizontal wells in Midland County specifically. Once again, type curves are area specific, and I'll go through a process of what was used for the area that I chose. I'll be perfectly honest, this is not an easy area. It's an area with an enormous number of wells, and that was chosen by design. And then at the end, what we're going to do is we're basically going to have built the type curve, and then we're going to run PHDwin economics on that representative type curve to understand what we could expect if we were to basically make another capital investment and drill another horizontal well, targeting the horizon that is going to be articulated and identified here. Okay, so we have a table of contents. I'm just going to point out that it's going to be relatively straightforward. It's going to be an introduction. Then I'm going to go through the various other components of the presentation in detail to some extent. Okay, so the first slide here that basically looks at from what the EIA put together, and this is a slide actually that in the very bottom left-hand corner, if you have an eye to be able to observe it, it says it's 2011. This was put together by the Energy Information Administration, and I have a copy of it from that perspective at that time. There are subsequent updates to it, but at the time, this was the unconventional resource basins in the United States that were being pursued in the lower 48. Now this here is from the EIA site. This is a very, very recent snapshot of it. And what I'm looking at, this here is in the last, well, I'm pretty sure it was August the 15th. It's in the last week. And what I'm looking at here is the EIA's website, specifically on the tight oil production in the Permian Basin and other areas in the United States. And you can see on the very right-hand corner here, on the right-hand scale, excuse me, on the chart, it basically has a color for the Permian, which is in light blue. There's the Bakken, the Eagle Ford, the Niobrara, Codell, the rest of the United States shale basins, and then the legacy lower 48 production. And this particular slide is only looking at crude oil production. It's not looking at the total liquids yield, just strictly the crude oil. There's a few key little spots that I'd like you to take away from it. Region number 1, which I've outlined, is basically the 2015-2016 oil price decline. Okay, and what occurred there in terms of productivity loss associated with persons being financially unable to afford to drill horizontal wells and basically sell the crude oil at a price to get a return. Then there was the COVID-19 little pandemic, and then ironically enough, it's very clear the Texas freeze that occurred in February of 2021 at the very end of COVID, or the starting of COVID coming to an end. And that was a material decline also that I highlighted in here. The point to make out on this slide, as you can see very clearly, is that the Permian Basin makes up a significant amount of the US's existing production. Now, this is the same EIA site. This is one of these standard tables that they have. You can go through it and basically pick things. All I've done is just made it a little bit easier to look at it. As of the date here, this is for July of 2025. It states that the tight oil production in the United States is just at 9 million barrels, and the Permian Basin makes approximately 5.7 million of it, with the other contributing areas being down here in the very, very bottom, as you can see, very flatlined relative to the Permian Basin's growth, which has significantly increased from 2000 and I'm looking at the scale here, it's 2016 to the present day. And the Permian has been highlighted. Now, we're going to talk about geologically what makes the Permian Basin so unique. It's a very, very unique arena. So fundamentally, the thing that basically we need to take into consideration is plate tectonics. Plate tectonics, looking at it relative to today, and what we're looking at here is a screen snapshot, and I have basically the location of where I captured this from. It's from the web, and basically what it shows the relative movements of the various plates relative to each other on the geography of what the world looks like today that we all recognize. Now, admittedly, it has not always looked like this. It's been fundamentally different in the past. So what we're going to go through is we're going to go through some slides that have been put together by Dr. Ron Blakey, and he basically has a website on it. This is something that I personally have been involved in looking at now for well over a decade. And all I'm going to do is I'm just going to go through a little screen snapshot. I'm going to describe what is on this slide, and then I'm going to go quickly through the other slides. But fundamentally, what we're dealing with here is we're dealing with plate tectonics. And in this particular case, we're going to be looking at the late Pennsylvanian, which is 300 million years ago, as it's been outlined here on the left-hand side in a red box. Now, what you'll notice in here, and it's a little subtle, but you'll be able to observe it, and that is basically you can see the outline for the lower 48. Okay, they're in a very, very light gray color. And what you can see is you can see Canada in the north. Okay, you can see Hudson's Bay that exists there. You can see parts of South America that exist. And what I've done is I've superimposed an outline in red at the very bottom center portion of the slide that basically is Texas, and what it looked like as it's being postulated based on geological paleo reconstructions of the late Pennsylvanian 300 million years ago. And what you'll notice in here in the Panhandle and in the West Texas portion, you'll notice that it's basically a portion of an interior seaway that runs into the central portion of the United States at the time. Now here in the early Permian, around 290 million years ago, so this is a 10 million year time span, you can see things have changed substantially. The outline of Texas is still there, and you can see basically the entrant from the open ocean to the very, very southwest portion of the slide into the interior portion of the United States, in which you can see a shallow sea. Now that shallow sea, in which makes up a significant portion of the western part of Texas and the Panhandle, basically is the originally portions of the Permian Basin at the time. Now we're going to move to the next slide, which is what the Permian Basin looked like at the middle Permian. Sorry, this is the late Permian. I take that back. That was the middle Permian. And what you'll notice is you'll notice that the land masses have changed. Once again, these are paleogeologic reconstructions based on plate tectonics and based on an unbelievable amount of data that Dr. Blakey has been working on for a lifetime, to be honest, with other geologists globally. And what you'll notice over here on the left-hand side is that you can see the outline of the central portion of the United States. You can clearly see Hudson's Bay. You can see the Great Lakes. Okay, you can see the Appalachian Mountains that are going in a northeast, southwesterly direction. Okay, and then you can see Texas that's still there. That seaway area that was in the middle Permian is now, over the course of 15 million years, is basically starting to dry up. What you'll notice on the left-hand side, the left-hand portion of North America, are these island arc chains. And these island arcs are what basically have collided into North America to actually create what we all recognize as the Western states. Now here we are at the early Triassic. So this is approximately another 15 million years time span. And you can see that the state of Texas now, you can see where the equator is. The equator is that white line that's there with the north arrow. That is the position of what North America looked like with these paleo reconstructions. Again, the Permian Basin's gone. There's no more deposition anymore at the early Triassic. That Permian Basin basically lasted for a period of approximately 50 million years. And in that 50 million year time frame, the horizons that we're targeting today have basically been deposited and preserved. The important part is preserved to the present day for us to basically focus upon them. And here at the end of the Permian, we had basically this gigantic extinction event. And this is basically a reconstruction of what Pangea looked like. Once again, this is a paleogeologic reconstruction. We got the Paleotethys Sea to the right. We've got North America. We've got Africa. We've got South America, Gondwana land, which was down here. Antarctica is down there. There's Australia. You can see Siberia at the very, very top. Now, the whole point is that Texas at that time, for all intents and purposes, there was no more deposition. That paleo supercontinent had been formed. The oceans that basically allowed the deposition of what exists now in the Permian Basin that we're targeting, the unconventional resources that generated all the hydrocarbons, is gone. Now, I'm just going to point out here, this is from the Bureau of Economic Geology, and this is a study that basically was put together and published. It was put together from starting in the late 90s, and it was published in the early 2000s. I believe it's around 2006. And what it is basically a snapshot of the various plays that have basically been identified geologically for the Permian Basin. And the thing that just to point out is that as of the end of 2000, the Permian Basin, the reservoirs that have basically been identified and were producing had produced just shy of 29 billion barrels. Now, I'm just going to point out that to the present day, over 30 billion barrels of oil has been produced from conventional plays. These are all conventional plays before the unconventional shale revolution started. Now, I'm just going to point out that the older geologists that were around, at the time frame in which the Permian was being developed, they were aware that this was the arena of an unbelievably prolific petroleum system that generated a very, very large volume of oil and gas. The difference is that it was known to be the source rock. It wasn't known as being a target, which is what we're doing today and what has literally transformed the United States from being in a position of not being energy self-sufficient, which was the case back in the latter half of the 1970s, in which we had all kinds of economic issues revolving around the fact that we weren't capable of producing domestically our source of crude, and we were basically held hostage by OPEC that raised the prices, to now being in a position that we are basically energy self-sufficient. And as a matter of fact, from gas, of course, we're actually exporting it. Now, this here is a slide, and I put it down here in the very bottom left-hand corner, basically the location of where I got it from. It was a presentation that was publicly available at the time by Pioneer, and it was their investor presentation of June 2017. It provides a cartoon, a very, very good cartoon, as a matter of fact, that goes through the salient geologic features that makes up the Permian Basin. Most of you, I'm sure, have seen this particular slide. I'm just going to talk about it. There was also in that same presentation, there was a three-dimensional isomeric that was basically built, providing persons with an understanding about the orientation. This is a view from the northwest. That's where the sediment source basically was substantially originating from into the Permian, the eastern shelf. It was coming from the Central Basin Platform, and it was coming from the Marathon Wichita orogeny to the south that basically deposited sediments into the basin. What you can see here is you can see the feeder channels, and you can see these basinal deposits that basically landed in the Permian Basin. And these are, of course, some of the classic gravity flows or turbidity currents that industry has focused on and observed over time. Now this here, once again, is from that same Pioneer presentation of June of 2017. It's an excellent slide. It basically goes through and provides a clarity of some very salient things to keep in mind. Of course, it hasn't changed. Geologically, nothing has changed. What has changed is our ability to actually look at it as a viable target. So at the time in June of 2017, 13 horizontal play intervals had been identified. 10 intervals had been tested successfully. 3 additional intervals remain to be tested. And I'll just point out here at the very bottom as to what the targets were that were remaining to be tested. For all intents and purposes, were the Barnett, okay, the Woodford, the Mississippian, and the Atoka had just been tested. And this is basically an outline of the various geologic targets that make up those 13 targets that Pioneer had geologically identified and tested, all of them except for 3. Now, this is a very, very important slide. It comes from the same presentation again. It's an incredibly salient presentation in that it provides a clarity of being able to compare the Permian Basin with the other unconventional resource basins that basically we target for oil and gas. Now, the Delaware Basin is right here. These are the geologic formations that are basically have been targeted and identified. The equivalent name of those particular formations in the Midland Basin basically are identified with a geophysical log of giving you an idea about just how thick it is. What I've done down here on the very bottom, that is a 200-foot scale, and comparing the Eagleford, and you can see here is there's 1, 2, so that basically is approximately 400 feet. Niobrara is 1, 2, 3, so it's approximately 600 feet. The Bakken is approximately 200 feet, with the Marcellus another 600 feet. Now we can compare that to what exists in the Permian Basin. What we're dealing with here is an unbelievable geological endowment that Mother Nature gave us to pursue, and that's the single largest reason why the Permian Basin has been focused on. The other basins are excellent too. There's no question. They just can't compete. Geologically, this basin is the center of the universe. Now, from a conventional standpoint, exploration looks for 5 crucial characteristics to establish a basin within a proven petroleum hydrocarbon system. On a professional basis, I've worked basically everything from production engineer, drilling and completions, including basically wildcat exploration in the deepwater Gulf of Mexico and other parts of the arena. And all I can tell you is the number one thing that geologically we're looking for to be able to establish the fact that we've got a chance to actually produce oil and gas in commercial quantities. The number one thing you got to have is thermal maturity of the source rock within the oil and gas window. The other things, timing and migration, structural relief, reservoir quality, and a seal, those are all required too. But that thermal maturity is what's really required. The Permian Basin, as demonstrated in that previous slide, okay, basically has over 3,000 feet of it. That's why it is such a prolific arena. Now we're going to talk about basically the basins, a little bit about the basin's production growth and identifying the assessments within the basin, as well as the inventory of future locations that admittedly I put together. And this is a few years ago, but the reality is for all intents and purposes, it's remained the same. However, I have basically made some changes to it. Now, this information all comes from the U.S. Geological Survey, the USGS, and what the USGS has done is they've conducted several assessments of undiscovered oil and gas formations in the Permian Basin of West Texas, and this includes basically 3 very, very salient studies about the Wolfcamp, shale and Bone Spring formations of the Delaware Basin. That was published in 2018. The Sprayberry Formation, which was 2017, and the Wolfcamp shale of the Midland Basin in 2016. We're going to briefly go through what the USGS actually put together in their assessment and what the implications of it is. Okay, I'm not obviously going to read this. This is publicly available. You can go to the USGS's website if you are interested in wanting to read it in more detail. But suffice to say, there is an intro to it. It's an assessment of undiscovered continuous oil resources in the Wolfcamp Shale of the Midland Basin. Okay, and this was published in 2016. It was the latter end of, each one of these were at the latter end of the relevant years. And this is an outline of what was put in place and a brief description of what was done. And for all intents and purposes, all I'm going to focus on is the aggregate sum of everything. Okay, and it goes through all of the different reservoirs. Okay, and I'm going to look at basically the statistical log normal mean. Okay, and this log normal mean has been highlighted here in red. It's the cumulative sum of basically the Wolfcamp A, Wolfcamp B, upper, Wolfcamp B lower, the Wolfcamp C, the Wolfcamp D, and then the northern portion of the Wolfcamp in the Midland Basin, the northern part. Cumulatively at the P50 mean, it's approximately 20 billion barrels of oil. 20 billion barrels of oil, and if we look over here at the gas and we look at the mean, it's about 16 TCF of gas. Okay, that's an enormous amount of resource. Now, I'm not going to go through it. It's exactly the same thing, but I'm just going to show you what we're going to focus on here. This is the Sprayberry. Okay, so now we've got approximately it's about 4.2 billion barrels of oil at the P50 mean, and then about 3 TCF of gas. Now, the one that is really the outstanding endowment of a resource is the Delaware Basin. Okay, they went through and basically looked at the Delaware Basin. The Delaware Basin had approximately what was defined at the P50 mean was 46 billion barrels of crude oil and 280 TCF of gas. Now, from the perspective of what exactly the USGS put in place, and all I've done is summarize it in a very simple little spreadsheet, and basically looked at the methodology that came out of the various studies there that I just pointed out. And that is looking at it in terms of the Wolfcamp A in the Midland Basin, the continuous acres that were put in place. And these are the units that the USGS used at that time. Now, criticism, it's an assessment methodology. And all I did was just basically revised it. And this was it was basically put together in 2019. And when it was first presented, and I looked at it at the time, and that the industry had basically been pursuing a strategy in which we were basically looking at six horizontal wells from a lateral spacing standpoint. Okay, not talking about the various benches for a given pad, but for this, we're talking about 1,280 acres, and there's basically 6 wells spaced out within that section-wide spacing. Now, what I did at the time is I put together an assessment here and looked at it in terms of if each rig, and there was a little qualifier over here in the red that I updated, but if each rig at that time was basically drilling 1 wellbore in 30 days, and that was admittedly kind of like the average at the time, we've substantially gone absolutely beyond that. But the time frame for development based on the resources that had been identified by the USGS and the spacing that they had in place, and the methodology that I put in place, which was basically, for all intents and purposes, 2-mile horizontals. Okay, we're looking at a time frame between somewhere around 80 and 40 years to develop it. Now, what I did do is I went and looked at Enverus. Okay, that's the data source that I use. I've used IHS in the past too, but Enverus is my favorite. And admittedly, in 2024, I looked at it. there were 308 wells that spudded 6,300 well bores in the Permian Basin. Okay. Now, with that in mind, that basically averages, it averages about 20 wells, about 20 and a half horizontal wells a year per rig, versus what I had over here, which was only 12. All right. So with that in mind, we've seen technological innovations in drilling rig bottom hole assemblies, bits, directional drilling mud motors, mud systems, etc. Okay. And basically we all are very familiar with the amount of innovations that have occurred over the time frame it's taken us to basically develop where we are sitting today, which I'm going to get into next. Now, what we're going to do is we're going to look at a methodology, okay, a very step-by-step one of looking at public data, okay, and how to create a representative type curve to run economics. Now, what I did look at here is the Permian Basin's the active producing horizontal wells. Okay, and what I'm just going to point out is that I just basically went through the drilling info's tabs in here. For those of you who use it, you'll be very familiar with it. And what I've done is basically picked the active number of well bores, and it's approximately 44,000 of them. And the reservoir list, which is listed over here, substantially is longer than what is able to be displayed. But fundamentally, these are the number of wells that exist in the Permian aged rocks, okay, that make up the Leonardian and the Guadalupian eras, in which we know about the Wolfcamp through the San Andreas and Clear Forks. Now, this here is a little screen snapshot, okay, of Midland, Texas. So you can see Midland, you can see Odessa, you can see Ector County, Martin County, and Midland County. Now, this little red box outlines, okay, prior to putting any wells in it, basically the arena that we're going to be looking at for a type curve. Now, this is what that arena looks like. Okay, these are the type curves these are the horizontal well bores. Admittedly, they're all straight lines. These are not plan view displays of a directional survey. The DI software makes it very, very simple here to look at it. You can, of course, look at it in a different viewpoint where you can see the plan view of it. But this is the outline of what we're looking at in red. Okay, now this is that outline in red, and this is the number of wells that exist. I'll just give you an idea. There's over 1,000. There's 1,000 horizontal well bores that exist in this area that was chosen. Okay, so what I've done with it is a methodological process that I go through personally in basically putting together a type curve. And admittedly, you can do this anywhere. It has nothing to do with being explicit to the Permian Basin by any stretch. It's anywhere you want to look at. And I won't deny that I picked an area that has a very large number of wells for a reason. And I wanted to make it so that it was something to take into consideration when you're looking at an area that has an enormous amount of data, an amount of details. So what I've done in here is basically taken the CSV file that basically you can download when you've conducted a search. And all I've done in here is I've gone in there and basically in that red outlined area, I've created an area of interest, captured all the well bores, and basically built a Excel spreadsheet out of it. It does provide it in a CSV file, but if any of you have looked at it, it's not the most pretty thing at all. It takes a little bit of time to basically make it what I call pretty and usable. And what I'm looking at here in particular is I'm keying off on active wells, and I'm keying off on their TVD depths as defined. Now, this is basically the area that I'm looking at. It's approximately 11 miles in an east-west direction, and north-south is about 10. I mean, but for all intents and purposes, you can see there's some blank spots in there. So I'm just saying it's 100 square miles. That's approximately 100 square miles. There's 804 active well bores in that 100 square miles, which is literally sitting right underneath. You can see there's Midland right under there, and there's Odessa just over here. Now, what I've done with it is basically put together a little graph. I will not deny that on a professional basis, I'm very visual. I need to be able to graph things and be able to see it. Okay, and there's no substitute for it. Objectively, what I'm looking at here is I graphed everything based on a January 1st, 1980 first production date, in this case here, and I just extended it to basically the end of 2025, knowingly that we don't have data to the end of 2025. But what I'm looking for is I'm looking for the TVD landing points of it, and I'm looking for the dates of first production. What you can clearly see is that the horizontal wellbores, for all intents and purposes, in that 100 square mile snapshot started approximately 2012, okay, the latter part of 2012 to the present day. And you can see the various TVD locations that have been targeted in that time frame. Now, the reason I showed this in here is because these wellbores that are here are from the late 1990s, early 2000s, and what they reflect is they reflect the Devonian gas wells that were drilled in this general area. Now, what I've done with that is I've basically taken all the TVDs of all those wells, and basically I'm looking at it, the objectives of what I have here. I'm not going to read through all of them, but fundamentally they're here for the purposes of you looking at it at your own leisure. But fundamentally what I'm looking for is I'm looking to basically decide, okay, how many bins there are, okay, in terms of TVDs, okay, and first production dates for the purposes of basically picking a subset of the data that I'm going to focus on. And what you'll see here is I've listed them with little bars on them as it relates. This one here is red, and that's landing horizon number 1, and that's the TVD depth range. It's approximately a 200-foot range, and you can see that here from this here is approximately the middle part of the end of 2021. Okay, and in this case here, what I've done is I've picked it to approximately June of 2024 for the purposes of having approximately 12 months of production. I need at least 12 months of production to have some degree of confidence in being able to look at the production profile of those wellbores. And so what I've highlighted is that there are 6 different landing zones that I've identified. Of course, other people would pick different numbers, but I've given you a clarity as to how I've done it. Okay, it's not an exact science. It is an exercise in basically consciously thinking about what you're looking for. What I've highlighted in here is I've highlighted approximately a time window, okay, that basically as around 2020, the end of 2021, okay, and basically what I have is a depth window of approximately 9,700 feet, okay, to around what is it? It's about 9,900 feet TVD, okay, and that area is what I'm going to be looking at in detail on the next slide. And the whole purpose is I'm going to basically show the methodology for targeting that horizon, and it's just a matter of rinse and repeat to do it on all the subsequent ones. So what I've looked at in here now is I've basically taken those wellbores in that TVD range, okay, and now what I've done, the TVD range is on the left-hand scale. Now what I've done on the right-hand scale is I put the horizontal lengths of the wellbores. Now, there's more than one way to do a type curve. There's no 2 ways around it. You can, of course, and many people do, whether they do it personally or they use some other software to do it. The issue is that you can basically do it on an EUR per foot. And so you can basically look at these and say, okay, what I'm going to do is I'm going to basically, I know that the TVD depth is this range right here. The fact that there is a horizontal length range between approximately 1.5 miles at the very bottom, okay, here to approximately 2.5, okay, is that you could go through there and do that. I have not. What I've decided to do is I basically bin them okay, consciously between what I call type curve number 1 area, which is right here, and I put the little dotted lines for it, and then type curve number 2, and that's approximately 90, it's actually about 9,600 feet to 11,100 feet. And that is the lateral lengths as defined by drilling info from the directional surveys that have been provided to the Railroad Commission. Now, what I've done with it is I've basically gone through that specific TVD depth horizon and those horizontal length horizons, and I've taken that spreadsheet that I've basically made look an awful lot prettier than what it originally looked like. And what I've done is I've explicitly looked at the drilling info lateral lengths that are here, and I've shaded those that are in excess of 11,000 feet in gray, and those that are less than 11,000 feet and approximately 9,600 feet in pink. All right, and that's for the purposes of visually being able to look at them. Now, from the perspective of what do they look like actually on the map, okay, the type curve number 1, which are the wells that are longer, okay, versus the wells that are a little bit shorter in that 100 square mile area. These are the well bores that basically target that 100-foot TVD interval between approximately mid-2021 to mid-2024, okay, and those horizontal lengths. That's what I'm targeting. Now, the reason I picked 2021 to 2024 is because that's what I would refer to as the present day, approximately the last rendition of the development cycles, okay, for the drilling, the casing, the completions, and putting on stream strategies. There have been numerous revisions that have occurred through time, especially since 2012, when I pointed out is when it first started here in this 100 square mile area to the present day. And what I've looked at is specifically focusing on the most recent wells that are utilizing the most what I would say consistent drilling and completion strategies and production strategies, so that any subsequent wellbore is not going to be basically burdened by the previous renditions of it. Now, what I've done is I've taken the data and basically imported it into PHDwin. Now, admittedly, I'll just point out that I'm using PHDwin's version 2. I have yet to basically make the effort to elevate myself to version 3. I will do that. I've made that a commitment to TRC consultants that I would do that. But in the meantime, I'm still using version 2. Now, what I just pointed out here is basically these are only the well bores that are the lengths that I chose, as I pointed out. Okay, approximately 9,600 to around 11,000 feet. Okay, and then what you'll notice in here when you look at the data is you'll notice that there's some errors that basically need to be fixed. Okay, so those errors are fixed so that I can basically go from the 27 well count that's in here to actually the well count, which is the usable well count, which turns out to be 22. Okay, and once again, at that lateral length, it says 95, but it's actually about 96, okay, to 11,000 feet. Okay, that's what we're looking at, and that same TVD window. They're all within 100 foot of each other, TVD, as defined by the output from. I didn't put this in three-dimensional space in an isometric cube to actually look at it. I don't think that's necessary. This is a very, very good approximation of choosing the right well bores that are representative of that TVD length. Now, what I'm looking at here is basically when I create a type curve out of it, normalized, as we all know, it's normalized to times 0. Okay. The thing is that what I look at in here is that this is what basically I look at for both the water production, the oil production, the gas production, the GOR, the cum oil and cum gas. Now, the thing is that some people may very well deem it that they're done. And I understand that. I'm just going to point out that in my opinion, you're not. And I'm going to explain what enhancement is required in order to go to the next level. Okay, so now what you look at in here from the perspective of basically looking at a type curve, one of the things that you got to look at is you got to look at the well count. If you're going to basically look at putting together a forecast on the basis of this normalized production, you're making the assumption that basically the well count remains the same. As you can clearly see that I've highlighted it here because I've removed the cumulative gas curve and instead added the well count curve. You can see that from a normalized basis, there is approximately 14 months, and I know this answer because you're going to see it here in more detail. It's about 14 months in which I've got 22 well bores. And then as I go through time, my well count goes all the way down to 1. Okay, now that, if you were to basically forecast that water, that gas, that oil, you're going to get an error. You're going to get an error because your well count is not stable. You got to have a stable well count. So now here's the thing. How do I create a representative type curve where the well count is stable and flat? Okay, well, the first thing you got to do is you got to go look at the data. All right, so this here is looking at the well bore that has 45 months. It's not the only one, but it's one of them. And that one's basically called window pane. It's that well bore. And this here is a projection on the water, the oil, the gas, and you can see that the GOR matches very nicely. I'll just point out that I use basically a terminal decline of 6% after the hyperbolic basically comes to an end. Now let's look at another well bore. This is a well bore that has 14 months of production. Okay, came on in approximately January of 2024. Now, obviously, it has been impacted by either a shut-in or an offset frac. Remember, they're all within 100-foot TVD landing depth. Okay, so is it a well bore that's adjacent to offset? I didn't look at it explicitly. If I needed to run really detailed economics because I'm drilling an offset in here, I would do that, but I didn't. But what you can see, what I put in here is a forecast. You can see that the well bore is coming back. Whether it actually recovers back to where it originally basically was prior to that shut-in or to that fracture interaction on an offset, or a combination of both, I've made a projection and suggesting that's going to come back. Of course, that has an impact on the EUR. Okay, and that's going to be taken into consideration. In this case here, some could say, Richard, you're being kind of generous. Maybe so. All I know is that I've looked at a lot of these, and they oftentimes do come back to some extent. And what I've done is I've given it the benefit of the doubt that it's going to make it back to this as of date, which happens to be August 1st, 2025. And the data is available here at the time as of May 2025. Now, building that representative type curve, what I have to do is I got to run the forecast for each one of those 22 well bores one by one. Now, will the well count be stable and flat? The answer is yeah, it will be. Now I'm going to create basically that type curve. Now the type curve is created by basically putting together the forecast on an individual well basis for each one of those well bores. Okay, now this is what it looks like. It's a nightmare. Okay, once again, I'm using the older version. It's the version 2, not the version 3. I'll figure out 3 here in the next few months, if not sooner. But in the meantime, I've used here, and I'm just showing an example of 2. Now, for the purposes of a type curve, it's created from the compiled forecast of 22 horizontal well bores selected based on TVD depth and lateral lengths. Okay, it looks awful, right? So now what do you have to do to fix it? And this is the point of basically going through step by step as identifying what needs to be done. Well, basically you got to edit the graph timeline. Okay, what happens is by default, PHDwin version 2 defaults it to a year normalized at year 1900. Okay, so what you have to do is you've got to basically edit it. Okay, so now what I've done is I've edited it, and you can see it basically starts here in 1901, and you can see the type curve. Okay, the well count, as you can see, is absolutely stable. It's no longer sequentially going down over that same 5-year time frame. Now it's flat. And the reason it's flat is because each one of the well bores have been forecasted one by one. All right. Some of them are great, some of them not so much. But each one of them is basically represented in here. Okay. And now when I look at the decline for the oil, for the gas, and for the water, it is correct in terms of a better estimate of how to basically estimate what you could expect statistically by taking the range of 22 well bores at the same TVD depth and a similar horizontal lengths. So now what you have to do here is you have to go through and you have to edit it by hand, okay, in terms of the initial production rate, the initial decline, and then put together a segment. Okay, so what I've done is I've basically shown this is for the gas, and I've highlighted it here in yellow. There are 4 segments that have been put together for the purposes of generating this match on that production for those normalized 22 well bores. All right. Then the process, of course, is repeated, and you do it for the oil and the water, and you can see the match that basically occurs through here. For oil, I've got 3 segments. Gas, once again, there was 4, and water, there's 2. All right. And I do forecast water, by the way, and there's a reason you'll see in a moment. Okay. So now what you have to do is you have to edit it in the basically to a economic limit, or an estimate of what you believe the economic limit could be. And in this case here, I figure it's going to last to around maybe 2055, 2060. And so what I've done is basically made sure that the forecasted decline, remember the terminal decline for each one of these, it's 5% on water, it's 6% on oil and gas, and the well count defined in purple is stable until I get here, in which basically well bores are dropping off. But I'm not going to have to forecast that far. Now what I have to do with it is I have to create an actual case. All right. And so I'm going to basically take, when you create that normalized type curve, it is inappropriate to use for economics. It doesn't run. So what I've done here is I've basically put together the copied case. And the copied case, the only thing that you want to keep in place is you want to keep in place the projections, right? And then what the projections basically provide you with is they provide you with what the curve looks like. And the thing that you need to edit is you need to edit the start date. Okay, in this case here, the start date is going to be moved to today, but you can see the start date, I boxed it in here, started at 1901. And that is, remember, these are the segments that make up the type curve. And what I've highlighted in here is you've got to also add the economics. Okay, so now when you add the economics, I get an ECL, an economic limit of approximately, oil is approximately 6.5 barrels a day, and it occurs somewhere around, let's see, it's the end of May. So let's just say June 1st of 2053 is what the economic limit was basically truncated at, versus the forecasted limit to a value of, in my case, I basically use a 50-year project life, or 1 for oil, 1 for water, and 1 for gas. Now I'm going to build an economic case out of it. And all I'm going to do is I'm just going to show you just the process that I personally would go through. Okay. And this has been fine-tuned obviously over years. And what we're looking at here is we're looking at an effective date. We're looking at an investment date, and we're looking at a production start date. Admittedly, if I'm doing detailed economics that basically take into consideration money, when I'm going to spend money, okay, and when I expect things to come on, I'm not going to basically have them lining up perfectly at August 1st. I just did this for the purposes of illustration. And all I've done here for gas is I've basically picked $2 an MCF. For those of you who work in the Midland Basin, you'll all recognize that the Waha hub, you know, not everybody's getting $2. The Waha hub's got a massive discount on it, but I threw in $2 because this is only a 2-phase flow versus a 3-phase flow. And so I decided that, you know, $2 is taking into consideration the processing fees. And here are all the different costs that I've used. Okay, they're all outlined. Okay, for basically oil, gas, and water. As I mentioned, I do forecast water because water costs money, and that need to be taken into consideration as well. Now here's the very end of it, and basically what we're looking at here is we're looking at a well that's approximately 2 miles long, approximately, and basically I'm looking at spending $7.5 million. Okay, you saw the effective dates and everything else. They are artificial. Okay, but based on a $7.5 million investment, I'm looking at about a payout of about 1.7 years and a rate of return of around 35%. I admit that I can't read the slide at the moment. It's very small at what I'm looking at, but I know it's approximately that, and that's good enough. Now, here is something that I thought I would share, that for those of you that basically would like to be able to compare to what Drilling Info provides as it relates to the CSV file that you can get, okay, from when you download basically an area of interest. And in my case here, I just want to do is I want to point out the PHDwin forecast to an EUR based on an economic truncation on the cost structures that I used before. Okay, these are all done one by one. Okay, now this here is basically what's provided by Drilling Info, and these are the EURs that are provided. And all I'm going to say is that those are basically calculated. I'm not 100% sure exactly what they use, but it's going to be, you can use basically machine learning, artificial intelligence, whatever you want to use. The issue is this is an output that they provide, and I wanted to provide a comparison. How does it compare? So when you do it one by one and look at it from an average, I get an average of around 390, say 2.5 thousand barrels. And based on my type curve and my economic limit, okay, remember, these are all economic limits too. This is the actual arithmetic average. Okay, it's 388. Okay, 2.6 versus approximately 2.6 again. Okay, and compare that to what was provided by the EUR forecasts associated. And what you can see right here very, very clearly is that they were basically done as of an effective August the 7th of this year. Okay, that was when I downloaded the CSV file and was working with it to put together this presentation. Now, all I'll point out is that this is an EUR based on that effective date, but the average comes out to being approximately 511,000 barrels and 2.2 BCF of gas versus what's done on an individual basis. And I'm just showing that for you for the purposes of basically keeping in mind that the variations can be quite substantial, and one needs to take that in consideration. Now, all I'm left with now is basically the closing comments, and all I'm just going to point out is that we've gone through the intro, we've gone through geologically why, we've gone through the USGS's assessment units for the various horizons that exist in the Permian Basin and the future drilling locations. We've gone through a step-by-step methodology about how to basically manage data and put together a representative type curve and run the economics for it. And now we're down to the closing comments. Those closing comments are, for all intents and purposes, I'm just going to start out with just pointing out why the Permian Basin is the center of the universe. And every OPEC member knows about it, and every oil minister on earth is aware of it, is because it's been a game changer to the United States. Okay, and we're currently producing about 5.7 million barrels, okay, of a 9 million barrel inventory from tight reservoirs, with the other reservoirs highlighted in here from the EIA. Now, all I'm going to point out is the Permian Basin produces about 60% of US's crude oil. Okay, geologically, the Permian Basin is both unique and a national treasure. The USGS has conducted critical statistical-based assessments of formation presence, quality, aerial distribution, and thickness studies to arrive at a remaining resource of approximately, cumulatively, 70 billion barrels of oil and 300 TCF of gas. Now, admittedly, those are from studies from 16, 17, and 18. Obviously, there's been some production in there. There's been no material changes, but what has occurred that is not included in here is the Barnett, okay, and other horizons that have basically been tested that the USGS has yet to put together studies. Admittedly, how they basically pan out, I'm not 100% sure. I don't think that they're going to make a material difference by virtue of their aerial extents relative to the horizons that basically make up that 70 billion barrels and 300 TCF. Okay, the inventory of future drilling locations will likely span 2+ decades, but given the hyperbolic decline of unconventional horizontal wells and the poorer geological quality of the remaining horizontal landing point targets, peak oil production has most likely been reached, as been articulated in recent press releases by several entities. Now, creating a representative type curve requires the time to ensure that you've correctly selected a valid subset of horizontal wellbores. Okay, never be too scared to basically delve into a very detailed arena. You'll be surprised at what you see if you haven't done it already. There are numerous considerations, including but not limited to TVD landing points, lateral and vertical spacings, offset depletion and the likelihood of a negative hydraulic fracture interaction, etc. Okay, now those things all occurred in that little 100 square mile postage stamp that I looked at. Okay, and I only looked at one out of 6 landing horizons that were actually performed. Now, performing economic analysis is crucial to ensuring that you achieve a rate of return that at least meets the cost of capital with a profit. Got to get a profit. Otherwise, the disappointment of not meeting financial targets will catch up with you and your organization. Remember to always underpromise and overdeliver. If you have any questions, I'm more than willing to answer them to the best of my ability. Thanks.